Hey everyone, welcome back to AK Electric DIY. Today's video is a special one because it's a requested from one of our subscribers living in Jamaica. He reached out after watching our 10 kilowatt-hour solar installation video, asking for guidance on setting up a system for her own home. So in this tutorial, I'm going to walk through the entire process, step by step, to help her and anyone else planning a 10 kilowatt hybrid setup get started the right way.
Before we begin the installation, let's review the complete set of components required for a 10 kilowatt hybrid solar system.
We have 18 high-efficiency, 595-watt bifacial N-type solar panels. These panels capture sunlight from both sides.
At the center of the system is the DEYE Sun-10K-SG02LP2-US-AM3 hybrid inverter, responsible for managing solar input, battery charging, and seamless switching between grid and backup power. Energy storage is handled by a 16 kilowatt-hour lithium battery pack, providing reliable backup capacity and long cycle life. A dedicated DC battery breaker is included for protection and service isolation. For the PV array, a 2-in, 2-out, 1000-volt DC combiner box consolidates panel strings and adds an extra layer of safety with integrated protection devices. On the AC side, we're using a dedicated distribution box equipped with an AC isolator, an under-over voltage protection relay, surge protection, and circuit breakers to ensure stable and safe operation. For installation, an L2 mounting structure supports the solar panel securely and provides the correct tilt for optimal energy production. Additional DC protection includes disconnect switches, breakers, and surge protection devices to safeguard the system from faults or surges. All wiring, including DC, AC, and grounding, must be sized appropriately and installed with certified MC4 connectors to maintain system reliability and performance. And finally, proper safety equipment, including PPE and insulated tools, is essential for a safe and professional installation. Before installing any component of a 10 kilowatt solar system, a thorough site assessment is essential to ensure maximum performance and long-term reliability. We begin by inspecting the roof condition. The structure must be solid, weather-tight, and capable of supporting the weight of the panels and mounting hardware. Next, we check the roof orientation. In most regions, south-facing installations provide the highest energy yield, but the exact direction and angle will depend on your location. We then measure the available space to confirm there is sufficient room for all 16 panels, while maintaining proper spacing and airflow. Sunlight exposure is another critical factor. The roof should receive strong, consistent sunlight throughout the day for optimal system output. Finally, we perform a shading analysis. Any obstruction that casts shadows on the solar array can significantly reduce energy production, especially during peak hours. A complete and accurate site assessment ensures the installation is safe, efficient, and perfectly optimized for long-term performance.
Before we begin installing any equipment, we need to verify that every part of the system is correctly sized. In this section, we'll run through the essential calculations: solar panel string sizing, voltage and current checks, DC protection ratings, battery capacity requirements, and all AC and DC cable specifications. Making sure these numbers are correct ensures the system operates safely, efficiently, and within the limits of the DEYE 10kW hybrid inverter. Let's start with the solar panel specifications and calculate the correct number of modules per string based on voltage, current, temperature effects, and the inverter's MPPT range. We'll now verify the electrical sizing step by step. I'll show each calculation on screen so you can follow along or reuse them. Start with the panel data. VMP equals 42.06 volts. VOC equals 50.56 volts. IMP equals 14.03 amps. And ISC equals 14.70 amps. The inverter accepts VMP between 150 and 425 volts. So the number of panels in series, N, must give a string VMP inside that window. So by VMP alone, acceptable series counts are 4 to 10 panels per string. Calculation 2. Cold case VOC check. We must ensure string VOC at cold temperatures does not exceed the inverter max of 500 volts. We use a conservative VOC temp coefficient, negative 0.29% per degree Celsius, and assume a cold case cell temp of 15 degrees Celsius. So the panel VOC at 15 degrees Celsius equals 52.026 volts. N equals 10 would give a cold VOC approximately 520 volts. That exceeds the inverter's 500 volts maximum. N equals 9 gives VOC approximately 468.24 volts and VMP approximately 378.54 volts, which fits comfortably. Calculation 3. Number of strings and currents. With 18 panels total, 2 strings of 9 panels each is clean and fits the inverter limits. So each string supplies approximately 14.03 amps. 2 parallel strings give approximately 28.06 amps operating current and approximately 29.4 amps short circuit current. Calculation 4. String fuse and combiner protection. We size string fuses at 1.25 times ISC to 18.4 amps using 20 amp PV rated fuses per string. Calculation 5. DC isolator and DC breaker. Combiner to inverter. Use a 1000 volt DC rated isolator, industry norm for extra margin, and a 32 amp DC breaker between combiner and inverter.
Calculation 6. DC SPD, PV side. Install a PV-rated DC SPD with continuous operating voltage, UC, greater than the PV VOC. In practice, use a 1000-volt DC SPD in the combiner box for reliable protection.
Calculation 7. Battery sizing and battery breaker. A 16 kilowatt-hour battery at 51.2 volts corresponds to about 312.5 amp-hours. If the inverter draws the full 10 kilowatts from the battery, the DC current is about 195 amperes. Therefore, the battery breaker and cable must safely carry that current. Calculation 8. Battery cable voltage drop example. With a 50 millimeter squared copper conductor over 2.5 meters, the round-trip voltage drop is about 0.34 volts, roughly 0.66% of 51.2 volts, which is excellent. If the run is longer, increase conductor size to keep drop low. Calculation 9. Array cabling, panel to combiner to inverter. Use 6 millimeter squared PV-rated cable per string, panel to combiner. From combiner to inverter, carrying both strings, use 10 millimeter squared copper for good practice. Increase conductor area if run length is long. That drop is very small relative to the string VMP, assimilates to 0.13%, so 10 millimeter squared is appropriate for short runs. Calculation 10. AC side, inverter output, and breaker. The inverter's 10 kilowatt AC output implies approximately 43.5 amps at 230 volts. Using a 125% continuous load rule gives a breaker near 54.3 amps, so a 63 amp AC breaker or isolator is a practical standard choice. Install a 63 amp AC isolator or MCB for the inverter feed, an AC SPD at the distribution board, and an under or over voltage relay set to the inverter utility recommended thresholds. Fit a bidirectional energy meter if you intend to export to the grid. Calculation 11. Summary table. That table captures the key electrical sizing decisions, chosen to keep voltages and currents inside inverter limits and to provide safe protection margins. With these calculations complete, we can confidently select the required breakers, SPDs, isolators, and cable sizes. Next, we'll move to the physical mounting and wiring steps, making these numbers real on the roof and in the electrical room.
Now that our site assessment and system calculations are complete, we can begin the physical installation of the solar array. We'll start with securing the mounting structure to the roof. Make sure the L2 rails are properly aligned, leveled, and firmly anchored. This creates a solid foundation for the entire system. With the rails in position, we can begin placing the solar panels. Set the first panel onto the rails and secure it using the end clamps. Each additional panel locks into place using mid clamps, ensuring a consistent spacing and strong mechanical grip. Continue this process until all panels are mounted. For this installation, we are using 18 590-watt bifacial N-type modules. These will be wired into 2 equal strings of 9 panels each. To build the series string, simply connect the positive output of one panel to the negative input of the next. Repeat this across all 9 modules until the entire string is complete. When finished, each string will have one final positive lead and one negative lead ready for connection. Before moving on, we'll assemble our MC4 connectors. Strip the ends of your 6mm solar cable, insert the conductor into the MC4 pin and crimp it securely. Once crimped, lock the connectors together to ensure a watertight and reliable DC connection. Now we can route the DC cables from the roof down to the combiner box. Always use UV-rated conduit, avoid sharp bends, and keep all DC wiring separated from AC conduits. The goal is to protect the cables from heat, weather, and mechanical damage while keeping the system as safe as possible. Inside the DC combiner box, install the protection devices for each string. We'll place a 20-amp PV fuse on the positive side of each string, followed by a 1,000-volt DC surge protection device. The combined output then passes through a 32-amp DC breaker. Finally, before the cables reach the inverter, we install an external 1,000-volt DC isolator. This allows us to disconnect the solar array quickly for maintenance or emergencies. From the combiner box, the protected DC output is routed to the hybrid inverter. Using 10mm solar cable, connect the positive conductor to the inverter's PV positive terminal and the negative conductor to the PV negative terminal. Double-check polarity and tighten all terminals to the recommended torque values. To complete the DC side, we'll establish proper grounding. Bond each solar panel frame to the mounting rails using grounding clips or bonding jumpers. Connect the rails to the main grounding conductor, which is tied to the ground rod. Finally, make sure the inverter chassis is also bonded to the same grounding system to ensure complete electrical safety and surge protection. At this stage, our solar array is fully installed, wired, protected, and grounded. With the DC side complete, we're now ready to move on to the battery installation and the AC wiring for the hybrid inverter.
With the solar array connected, we can now move on to the battery installation. For this system, we're using a 16 kilowatt-hour Life battery bank, which provides long cycle life, high safety, and excellent energy storage capacity. Begin by placing the battery in a cool, dry, well-ventilated area. Ensure that the battery cabinet is level and secure, and that there is adequate clearance for airflow and maintenance. Never install the battery in direct sunlight or near moisture. Next, we'll prepare the DC cables. For a high-current battery bank like this, we use heavy-gauge conductors, typically 50mm copper cables, to safely carry the battery discharge current. Double-check that the cable lugs are crimped tightly and that the heat shrink insulation is properly applied to prevent accidental contact. Now we can connect the battery to the hybrid inverter. Start by switching the battery's breaker or isolator to the off position. Connect the positive cable to the inverter's battery positive terminal and the negative cable to the battery negative terminal. Always use the torque specifications provided by the manufacturer to ensure a solid and safe electrical connection. Between the battery and the inverter, we install a 250-amp DC breaker. This breaker provides essential overcurrent protection and allows you to isolate the battery during service or emergency shutdowns. Once the breaker is installed and the cables are secured, go ahead and bond the battery cabinet to the system's grounding network. With the wiring complete, we can now power on the battery and verify communication with the hybrid inverter. The DEYE system will automatically detect the battery's voltage, state of charge, and BMS communication. At this stage, the battery is fully integrated into the DC side of the hybrid energy system.
With the battery and solar DC wiring complete, it's time to connect the hybrid inverter to the AC distribution system. This section handles all grid, load, and backup circuits, so accuracy and safety are critical. First, we'll establish the AC output wiring. Run appropriately sized conductors, typically 10 mm copper or sized according to local code, from the inverter to the dedicated AC distribution board. This board contains the main protective devices for both grid input and load output. On the backup or load side, we install a 63 amp AC breaker to protect the inverter's output circuit. From the breaker, the load wiring goes to the essential load subpanel or ATS, depending on how the system is configured. This ensures stable and protected power delivery to critical home circuits during both grid and solar operation. On the grid input side, connect the AC supply from your main service panel through an under-voltage and over-voltage relay. This relay monitors line conditions and protects the inverter from unstable grid voltage. After the relay, install a Type 2 AC surge protection device to guard against grid spikes and lightning events. Next, route the AC neutral and ground conductors to their dedicated bus bars. The inverter chassis ground must be bonded to the same grounding system as the PV array and the battery to maintain a single, unified grounding network throughout the installation. If you're using an automatic transfer switch, connect the inverter's backup output to the ATS input, and from the ATS output to the essential loads panel. This ensures seamless switching between grid and inverter power without interruption. Once all AC breakers, SPDs, isolators, and relays are installed and tightened, double-check every termination. Verify that line, neutral, and ground are correctly positioned and that the wiring routes are clean, organized, and free from sharp bends. With the AC side connected, the hybrid inverter is now fully integrated into the home's electrical system. In the next stage, we'll power up the entire system, run safety checks, and begin commissioning the 10 kilowatt hybrid solar installation.
With all DC and AC wiring now complete, we can move into the commissioning phase. This is where we carefully bring the system online for the first time and verify that every component is operating within safe parameters. Before powering anything, begin with a full visual inspection. Check every DC and AC termination, confirm torque settings, and ensure that all breakers, isolators, fuses, and surge protectors are correctly installed. Verify the polarity is correct on all DC circuits and that grounding is continuous across the panels, inverter, and battery. Next, ensure that all system breakers are in the off position. Start by turning on the battery breaker or isolator. The battery will power up the inverter's internal electronics, and the DYE hybrid inverter should boot up automatically. Allow the system a moment to initialize and perform its self-check. Once initialization is complete, we can bring the PV system online. Turn on the DC isolator, followed by the DC breakers inside the combiner box. The inverter should begin detecting the solar voltage on each MPPT channel. If the readings are consistent with your calculated open circuit values, the PV side is ready to operate. Now it's time to energize the AC side. Switch on the AC output breaker first, which supplies power to the home's essential load circuits, or the ATS. Then turn on the AC grid input breaker. The inverter will recognize the grid waveform, synchronize, and prepare to operate in hybrid mode. At this point, the inverter should display live data from the battery, PV panels, and the grid. Confirm that the battery is communicating with the inverter via the BMS interface and that charge parameters match the manufacturer's recommended values. With the system fully powered, we've successfully completed the commissioning phase. The next step is to configure operational settings and verify real-time performance using the DYE monitoring platform.
Now that the system is up and running, our final step is configuring the settings and monitoring the system's performance. This ensures long-term stability, safety, and optimal energy production. Begin by navigating to the inverter's system menu. Set the battery type to LiFePO₄, or select the compatible BMS profile if the battery supports CAN or RS-485 communication. The inverter will automatically read the recommended charge and discharge limits from the battery's BMS. Next, set the operating mode. For most homes, hybrid mode, or solar first, provides the ideal balance between self-consumption and backup readiness. You can also customize time of use charging, grid charge permissions, and load shedding priorities depending on your utility rates and backup needs. Once the operating mode is configured, verify the PV input readings. Check each MPPT string for proper voltage and current levels. If one string shows significantly lower values, inspect the panels for shading, loose connections, or isolator issues. Now let's check AC performance. Review the grid input voltage, frequency, and load distribution. Ensure that the backup circuits are receiving power and that the ATS is switching cleanly between grid and inverter supply if one is installed. With system data confirmed on the inverter screen, we move to remote monitoring. Connect the inverter to Wi-Fi or Ethernet and open the DYE monitoring platform or mobile app. Here you can view real-time solar production, battery status, grid interaction, and historical data. Finally, perform a backup test. Disconnect the grid breaker to simulate an outage. The inverter should instantly switch to battery and solar mode without interruption. Verify that all essential loads remain powered and that the battery discharge rate matches the load demand. Once these checks are complete, your 10-kilowatt hybrid solar system is fully operational and ready for long-term use. This concludes the installation, configuration, and commissioning process, delivering clean, reliable energy to your home.
Now that the installation, commissioning, and system setup are complete, let's finish with some important tips, safety guidelines, and regular maintenance practices. These will help ensure long-term performance, safety, and reliability of your 10-kilowatt hybrid solar system. First, always remember that a solar energy system contains high voltage on both the DC and AC sides. Never perform maintenance during the daytime without isolating the PV array using the DC disconnect. And if you're ever unsure about a component or a measurement, consult a licensed solar technician. For routine maintenance, begin with a simple visual inspection every 3 to 6 months. Check for loose conduits, damaged cables, or corrosion on connectors. Ensure that the mounting structure remains secure and that no hardware has loosened due to wind or thermal expansion. Next, take a look at the panels themselves. In most climates, especially tropical regions like Jamaica, panels stay relatively clean thanks to rainfall. However, if you notice accumulated dust, salt, or bird droppings, gently clean the surface using soft water and a microfiber brush. Avoid detergents, abrasive pads, or pressure washers, as these can damage the glass or void warranties. Monitoring your system is equally important. Keep an eye on the DEYE app or web portal. Any sudden drop in PV production or abnormal battery behavior is usually a sign of a loose connection, shading issue, or a protective device tripping. Address these signs early to prevent long-term damage. Also check your surge protection devices periodically. Many SPD units feature an indicator window. If the color changes from green to red, the device has absorbed a surge and must be replaced immediately to maintain system safety. For the battery, ensure proper ventilation around the cabinet and avoid exposing it to extreme temperatures. LiFePO batteries are very stable, but maintaining a cool environment extends cycle life and keeps the BMS operating efficiently. Once a year, it's a good idea to verify torque on all critical electrical terminals, including the inverter, battery lugs, and AC breakers. Over time, thermal expansion can loosen connections, increasing resistance and generating heat. Finally, always keep detailed documentation. Record your installation parameters, breaker sizes, cable gauges, and string voltages. This information becomes invaluable for troubleshooting or upgrading the system in the future. With these simple maintenance steps and safety practices, your solar system will continue delivering clean, reliable energy for many years. Congratulations on completing this entire installation journey.
And thank you for joining us in building a smarter, more resilient, and energy-independent home.
And that brings us to the end of this complete 10 kilowatt hybrid solar installation walkthrough. From selecting the right components, to wiring the DC and AC sides, to commissioning, testing, and maintaining your system, you now have the full blueprint to confidently install and operate a high-performance solar power setup. I want to give a special thanks to our subscriber from Jamaica who requested this video. Your message inspired this entire tutorial, and I hope it helps you and many others achieve clean, reliable energy independence. If you found this guide helpful, don't forget to give this video a thumbs up. It really helps the channel grow. And if you're new here, hit that subscribe button and turn on notifications so you never miss another DIY solar project, wiring tutorial, or a system review. Drop your questions in the comments below. I respond to as many as I can. And if you'd like a full downloadable checklist or wiring diagram for this system, let me know and I'll make it available in a future video. Thanks again for watching AK Electric DIY. Stay safe, stay powered, and I'll see you in the next project.